Okay, thank you, Boumediene. So as Boumediene said, yes, today we're going to be talking about fictitious play and reinforcement learning. So for those of you who were there in the previous iteration of these sessions, we talked about some of the motivation of game theory, a little bit on how it works, and also introduced learning on game theory. And specifically, we were looking at three particular algorithms, right? Or adaptation protocols, whatever you want to call them. They were the replicator dynamic, fictitious play, and Q-learning. Yeah. So in the last one, we talked about the replicator dynamic. You may or may not recall that the dynamic looked a little bit like this, where essentially you had two terms. This right-hand term was all about the preference of the preference of the agent to choose actions that perform better than ones that don't, right? So this is in some sense like a rational part of their behavior. And then this term at the front encodes a little bit of stubbornness into, I mean, I like to think of it as encoding a little bit of stubbornness into the system, which essentially says that if the probability of playing an action is high to begin with, then it should still be high in the next time step. Yeah. And this is how agents adapt. Now, in this particular talk, I want to be focusing on fictitious play and Q-learning. And also, if I remember correctly, many of you were interested in the population adaptation side of the talk, specifically things of what happens when we throw in a few more agents rather than just two agents in our analysis. And although we won't be going into the depths of that today, I did want to put in a few comments on issues of learning and adaptation on populations. So we'll be looking, I guess, a little bit of a teaser into those before we move on to the actual population adaptation stuff in the next session. So without further ado, fictitious play and Q-learning. I'm going to start with fictitious play. So this particular algorithm or learning dynamic, whatever you want to call it, was produced or invented or discovered, depending on which side of the debate you fall on, in 1951. So around about the same time that Nash was doing his own proof of the existence of the equilibrium in all finite games. Fictitious play was, I guess I'm going to go with invented, as a natural way to approximate this Nash equilibrium. So a way to find the Nash equilibrium. And it works as follows. You have two steps. The first is creating each agent. Let's say it's myself and you. We're going to create a model of each other. And then I'm going to respond optimally to that behavior, to my model of what you do, right? This is pretty typical in learning in general, but what's specific is how we create the model and how we respond optimally. And it wouldn't be maths if we didn't take this simple idea and make it abstract. So let's do that. So the first step, creating a model of my opponent. Let's say I'm playing this rock, paper, scissors game against you, right? And at every single time step, I'm going to play some action I, and you're going to play some action J, right? So it could be in the first iteration, I play rock, you play scissors, and then so on and so forth for each of the other iterations, right? So the way that I would encode that is by writing in a pure strategy. If you guys remember from the last talk, we talked about how when we're encoding the state of an agent, what we do is we encode the probabilities by which they play particular actions, right? So in particular, let's say my strategy is at time K is this XK. Then let's say what did I say before? I play rock and you played scissors, right? So the way that I would encode that is I put a 1 at the top and zeros everywhere else. So this is my probability of playing rock. paper and scissors. And then similarly, you're going to take an action. I think I said that you had played scissors. So yours would look something like this. So this is the strategy that you have actually played at time step K. And the way that I'm going to build my model of your behavior is I'm going to keep track of what you've been doing up until the current time step. And I'm just going to take an average of that. Okay, so just to encode that properly, the way that I would do that is I'd add up all of your actions from, I shouldn't use K there, I should use I there, from I equals 1 to K minus 1, so up to the current time step, and divide through by 1 over K. Yeah, and that gives me QK, which is essentially my model of how you choose your actions, the probabilities by which you're going to choose your actions. Similarly, you're going to do that process for me, and you're going to get something that looks a little something like this, right? Now, as far as I'm concerned, all I have to see is QK, and all you have to see is PK. That's all we see of each other, right? Now we need to think about how we're actually going to respond optimally to one another. So for this second step, I want to take a slight detour. It's all going to tie in the next slide, but I want to take a slight detour into what's called the best response function. Something that we didn't quite cover in the last talk, but it's quite fundamental to game theory and particularly useful for the fictitious play dynamic. So the best response essentially says it's a function that takes your strategy. Let's say you're playing some strategy Q, right? And all it's going to do is it's going to assign the strategy or one of my strategies that would maximize my payoff. I hope that makes sense. So it's going to look at what strategy you played and take the argmax of the possible payoffs that I could get from my own strategies. Okay, and you would have your own best response function that looks at my strategy P, and you're going to find a strategy which maximizes your payoff according to what I'm doing, right? Now, the reason why the best response function is useful is because it gives us a way to think about responding optimally, because essentially it says that whatever your strategy is, I'm just going to take the strategy that maximizes my payoff. And in fact, it's a really useful way in which to define the Nash equilibrium. We looked at the Nash equilibrium last time, but let's write down like a really formal definition of it. If I have some strategy P and Q, I'm going to put some bars on it just to make sure it looks like an equilibrium. What the Nash equilibrium condition says is that my strategy P is basically just going to be a best response to your strategy Q, and yours is going to be a best response to my strategy P, right? Fairly simple idea, essentially saying as long as you play some optimal strategy for yourself, I'm going to do the same. And as long as we do that, neither of us are going to change our behavior. Now, the thing about this definition and this way of looking at equilibria in general, remember the Nash equilibrium is basically the object of study in a lot of economics, or at least it was. Because the notion was that we can assume that agents will eventually reach a Nash equilibrium and they will play according to the Nash equilibrium. So if I want to know what's going to happen in a particular interactive situation, all I need to do is model the game, find the Nash equilibrium of this game, and I know what's going to happen, right? We challenged this assumption last time by looking at replicator dynamic and showed that adaptation doesn't always reach a Nash equilibrium. But personally, I think there's a number of other problems with it. If we look at this definition, at no point does one agent say, I'm also going to look at, maximizing some kind of social benefit. All I care about in this is maximizing my payoff, and I'm assuming that you're going to only care about maximizing your payoff, which seems like almost a, I want to say sadistic way of looking at the problem, because you can think of examples in which this doesn't hold, right? Let's take classic example, parents with their children. For the most part, a parent would naturally be willing to sacrifice their own payoff, if we're going to put this into game theoretic terms, so that the payoff of the child is increased, right? So interactions are not always going to be purely selfish, which is why the Nash equilibrium isn't always going to be a good model for what an interactive situation is going to result in. That said, it is an easier equilibrium to study because it means that once you're in that situation, you can assume that agents aren't going to change their behavior. The whole idea of the Nash equilibrium is once we're playing this strategy, there's no reason for us to deviate from it, right? So it does make the analysis a little bit easier. And whilst this may not be useful necessarily for social situations, the nice thing about it is that we can design computational agents that would satisfy this sort of behavior, that would behave in quite a rational manner and might actually only care about minimizing their own cost or maximizing their own payoff. This is how most of control theory is designed, with the intent of each agent minimizing their own objective function or maximizing some kind of payoff function, right? Anyway, that's an aside on the Nash equilibrium and where it's useful. How does this fit back into our model of fictitious play? Well, remember, we had a model of our opponents. So you had a model of me, which was PK, and I had a model of you, which was QK. And as you might imagine, what fictitious play requires is I'm just going to play the best response to my model of you, and you're going to play the best response to your model of me. Okay? That, in a nutshell, is not even a nutshell, that is fictitious play. Just this idea of I will take an average of your behavior up until now, and I will play optimally according to this average. Are there any questions just based off that, as well as my incredible tangent on the Nash equilibrium?
Yeah, I wonder if I take what you're saying and I try to understand it in terms of prisoner's dilemma or multi-armed bandit, this picture that you portray stands on itself very well and makes a lot of sense and everything. Yet, there is something tricky about game theory that is sometimes counterintuitive. And the two examples I wanted to relate to are examples of that. And yet, people have discussions in certain contexts, okay? Like you take now this game of paper and so rock and so on, and just talk in that frame, right? So is there a way to say, I absorb what you say, I agree with it 100%, and now I want to compare it to what I understood from prisoner's dilemma. There is, in both, you have payoff made, right? But in prisoner's dilemma, the two captives are actually playing against the one who caught them, right? And against each other, but with the conclusion they have to collaborate or cooperate. Whereas here, I have to beat you and you have to beat me, right? So is there something else to say, or because maybe it's too long questions here?
To be honest, I'm not entirely sure what you're asking. Could you just elaborate a little bit on what you're asking here?
Well, there's certain frameworks of game theory that each stands on its own. But if I want to take a general view of the whole thing, to sum up everything, I can get confused.
Right.
So it just may be a comment. It's not a question with a solution. There is maybe no solution to it. There is different views at different situations, but at least it's relevant to stress the difference in
So
these
you're saying that
situations.
in each of these situations is almost like a restriction of a much more complex situation. And so on its own, you can analyze it, but then as you add, if you try looking at it in the wider context, it becomes much more complicated.
Exactly, yeah.
I think that's true. I remember in the last one, I kind of framed game theory as a thought experiment, right? But a thought experiment that gives you some information, or at least a way of thinking about a much more complex interaction. And so in a very typical fashion, you do have to, make all the necessary caveats to say that we're looking at this particular example with these particular assumptions. But it does give you some information that you can apply to a much more complex, realistic scenario, right? But our goal in dynamics of games in general is to try and move a little bit away from the restrictions and applying the concept of learning itself is an adaptation is placing things in a much more realistic context, right? And so hopefully with time, the analysis will start to move from, these restrictive cases where things are almost entirely known towards more realistic scenarios viewed in their whole, right? That would be the dream, essentially.
Yeah, that's a nice way out. Thank you.
Okay, so as I said about fictitious play, the whole reason why it was created or discovered, whatever you want to go for, is because it was viewed as a natural way to approximate the Nash equilibrium. And you might be able to see it directly from the discrete version that I just talked about. But personally, I find it a lot easier to understand fictitious play. And in fact, a lot of the analysis is much easier when you move from fictitious play in discrete time to fictitious play in continuous time, right? So what we're going to do is go from this algorithm to a continuous time approximation of it, right? And the way that you would do that is essentially by following the exact same set of steps, where if you remember, we were about to take an average over all of our states up until the current time step, right? And if I want to move into continuous time, all I have to do is, well, essentially the exact same process, where I'm going to be looking at my average up until time t, which of course I have to divide through by 1/t, and then the summand turns into an integral up until the current time step, right? So fairly intuitive, an immediate notion of how you would do that. And of course, this is the same for the second agent. And again, we had the same requirement that at any time xt, I have to be playing the best response to u. Okay. Now, what this allows us to do is move from an algorithm to a dynamical system that an algorithm to a differential equation that we can actually analyze, okay? And the way that you would do that is simply by taking this form here and just differentiating it. And it turns out if you differentiate, you get an ODE which looks something like this. You take the 1 over t and you have an XS that comes out thanks to calculus. And another term just from the chain rule, right? And you can essentially go through the entire process by moving xt from here into, it should be a t, into my differential equation, that you get a dynamic that looks a little something like this, right? And similarly, the dynamic for the second agent looks almost identical. Now, the reason why this is a little bit easier to analyze can be seen immediately from this point of fictitious play allows you to approximate Nash equilibria, right? The way that we would see that is, let's have a look at the fixed points of this dynamical system, right? The fixed points are essentially where these left-hand sides go to 0, right? Which, of course, when you rearrange, this 1 over t goes away because t is obviously greater than 0. And you get a result that looks like this, right? And similarly for the other agent. This was exactly the Nash equilibrium condition that we had beforehand, right? From our discussion of best responses, which means that the fixed points of fictitious play are exactly the Nash equilibria of the game. And that is a very useful thing for us to have, because that means if I analyze the trajectory of fictitious play, if it reaches a fixed point, then I know that that fixed point is a Nash equilibrium. Of course, if you're doing this computationally, this is in the infinite time limit, so you're going to be approximating it and you're going to be getting quite close to it, right? But then our whole question now has to be moving away from what are the Nash equilibria of the game to what are when does fictitious play reach a fixed point? Okay. I just did that. So one of the prototypical examples, we looked at zero-sum games in the previous lecture, and these show up basically everywhere in game theory, because they are almost not only are they the simplest, in quotation marks, to analyze, but also they encode pure competition, which a lot of games revolve around, right? So things like, as you said, Prisoner's Dilemma, both agents are working against each other. Similarly, rock, paper, scissors, we're both trying to beat each other. The example that I'm showing you right now is one of the ones that we looked at last time, which was the matching pennies game. But it doesn't really matter. All of this holds for any zero-sum game, okay? And if you remember the replicator dynamic, when we looked at this matching pennies game, it gave these orbits, right? These periodic orbits that never settle down to an equilibrium. Now, if you apply fictitious play in the exact same game, you get what you see on the left here, where instead of cycling down and never reaching an equilibrium, all of the strategies end up spiraling down to an equilibrium in the center, right? In particular, because it reaches a fixed point, we know that it's going to be converging to a Nash equilibrium from our previous discussion. Yeah, and this is a particular case for zero-sum games, but there have been other studies that looked at other types of games, such as ones in which both agents share the exact same payoff. So this is almost purely cooperative, or identical interests, as it's sometimes called, right? And similar results hold in those cases. But let's look at zero-sum to begin with, just because these were the first results. In fact, the convergence result for fictitious play in zero-sum games, I think, came out in the exact same paper as fictitious play was first introduced. So it was very immediate, right? Now, the reason that we know this, so I've shown it to you experimentally, but the reason that we know this in an analytic sense revolves around convergence results. And to be honest, the proof of the convergence isn't too horrible. It revolves around the use of what's called a Lyapunov function. Now, I'm sure most of you have looked at dynamical systems before, but just in case, a Lyapunov function encodes a notion of energy dissipation along trajectories. I'm going to be giving a very, very heuristic definition of what a Lyapunov function is. So anyone who does dynamical systems will probably scoff at me, but you're all muted, so I won't hear you scoff, so it's fine. A Lyapunov function essentially says that it takes this idea that as a particle moves along a trajectory, it dissipates energy until eventually, it stops, right? In a similar way, if you take any particular trajectory of fictitious play, right, or any particular dynamical systems, you don't need a physical form of energy. You can abstract it to this potential function, which, as long as it dissipates along these trajectories, you know that eventually the trajectory is going to stop and reach a fixed point at the end, right? And we encode that with what are called Lyapunov functions, which essentially, if they go to 0, that means that we've reached a fixed point of the dynamic, right? Again, heuristic definition, but it suffices for what we're about to say. So in particular for fictitious play, what does a Lyapunov function look like? Because, as I said, there's no such thing as energy, right? In this particular scenario. But the corollary that we have is essentially we look at the, that should be a Y, we look at the maximum possible payoff that each agent could get, right? This should be P dot By. Okay, so this first term essentially gives you the maximum payoff that agent 1 could get if the opponent is playing Q. And the second term gives you the maximum possible payoff that agent 2 could get if I'm playing P, right? Now, if we analyze this function and look at its derivative as, a fictitious play continues and as the trajectories evolve, what we'll end up finding is that this goes down to 0. And as we just said, if these Lyapunov functions go down to 0, we know that we've reached a fixed point, right? So because of our discussion on fictitious play to begin with, we know that not only does it reach just any fixed point, it reaches a Nash equilibrium. And the whole proof structure of this, honestly, it only takes like 5 lines. It's not super difficult, but what it allows us to do is abstract this, as we'll see quite soon, to much more complicated situations, right? But at the very least, now we know that if we're faced with a zero-sum game, if I want to know what the Nash equilibrium is, there's 2 ways that I could go about this. Either I could, take out pen and paper and try and work everything out by hand, or I could grab my computer, implement fictitious play, and just approximate it within minutes, right? And this is super useful when you have, we've been looking at 2x2 2-action games, even 2-player 3-action games so far. You could probably do that analytically quite quickly. But when you have multiple players or 50 plus actions that these players could take, that's when it's a little bit easier to use an algorithm to approximate the Nash equilibrium rather than, trying to do it all by hand. And this result gives us a really good start to ensuring that when we run fictitious play, we're actually going to get the result that we need. Now, is this always going to be the case? Well, that was shown to be false by this wonderful gentleman, a man by the name of Lloyd Shapley, who was a Nobel Prize winner, actually. And he, again, depending on which side of the debate you fall on, either invented or discovered a particular game in which fictitious play isn't actually going to converge down to an equilibrium. This type of game, this bimatrix game, A beta, B beta, as you can see, is parameterized by beta, right? But in particular, what Shapley showed that when you choose beta equal to 0, this very particular example of beta equal to 0 in both agents, what ends up happening with fictitious play is that the agents reach a limit cycle, right? Where they end up cycling around the Nash equilibrium. Actually, the Nash equilibrium for this game is right in the center. But both agents will keep cycling around this equilibrium and never actually settle down, right? And obviously the same is true for the other agent. This whole family of games is now called the Shapley family in his honor. And this was shown in the early 2000s, I'm going to say early 2000s, for various values of beta to actually give rise to the entire spectrum of possible dynamical behaviors, right? So we've already seen limit cycles in this family. It turns out if you choose beta equal to a very particular number, in fact, it's the golden ratio. If you choose beta equal to the golden ratio, fictitious play will converge down to a Nash equilibrium. But across this entire spectrum of beta, just ranging from 0 to 1, you can actually get fixed point behavior, as we just said, limit cycle behavior, as we just seen, and also chaotic behavior. Now, I'm not going to go into the details of that, mainly because that's one of Sebastian's results, and he did talk about it in his earlier talk on learning dynamics, which I think is up on the YouTube page for the SIG. So you should definitely check that out when you get a chance. But the whole point of this is now we can say for certain that, you know, we can't take convergence as, you know, for granted, right? That's what I'm trying to say. You can't take convergence for granted. We can't always assume that if we just run fictitious play, we're going to go down to a Nash equilibrium. Same situation was for the replicated dynamic, right? We couldn't just take for granted the fact that, you know, if we run this adaptation protocol, that agents are going to go down to a Nash equilibrium. So that kind of covers fictitious play in these two-player games. Are there any questions just based off that?
Yeah, I think there was a question on the chat.
Oh, okay. Sorry, I can't see the chat. Let me move over there. Oh, what happens if you have several Nash equilibrium points? That's a really good question. In fact, if you have several Nash equilibria, then that for the fictitious play dynamic, what that's saying is you have multiple fixed points for this dynamic, right? So depending on your initial condition, you might converge to a different Nash equilibrium. It's not rare, but it's very often the case that you would have multiple Nash equilibria in a game as opposed to just one. And there's another question. Oh, right, this is the conversation that we had earlier regarding the prisoner's dilemma. Are there any other questions on fictitious play in two-player games?
Yeah.
Yeah.
Is there, it's not a nice way to say it, but this is early morning for me, so I'm not so smooth. Is there a way to reverse engineer Shapley, with all due respect, in the sense that your previous picture where you had the zero-sum game on the left with convergence, no, one more, that's it. So on the left, we had the zero-sum games, and on the right, we had the limit cycle, right? So is there a way to go through the mind of Shapley and say, I look at this and I look at this, and how can I merge these two pictures? And this way, I put in the limit cycle view, I put zero-sum game, and then I get those, if you want, instead of this orbits forever, I get the triangles forever and no down spiral convergence.
So are you saying, is there a way to design a game in which you will always get this, like, you know what behavior you want a priori and you want to design the game to produce that behavior?
Yeah, specifically, I want to really understand Shapley, not only the result, but how he got the result. And
Okay.
somehow in my mind, I say, well, I can reverse engineer his thinking by trying to reconcile or converge these two pictures. And this way, I get the zero-sum game in the context of limit cycle, not in the convergence of the spiral.
Okay, so a couple of things. Firstly, the Shapley game isn't a zero-sum game. It was just a particular example of a game in which it was the first example of a game in which fictitious play doesn't converge. So just as a broad statement, for all zero-sum games, we know that fictitious play is going to converge thanks to the convergence result that we had earlier. Now, as to your question of how essentially do we go from, essentially how do we know that Shapley's game will reach that limit cycle, or how can we reverse engineer that? That's a much more difficult question, actually, and one that, to be honest, I don't think I can answer immediately. There is like the proof of the Shapley game reaching these polygons or this triangle. To be honest, I'm not sure whether it was found analytically or he ran a couple of experiments until he found it. But I always learnt it from kind of an a posteriori way of saying, I know that this result exists. What's the proof of it? So as to how we would go almost from first principles to say, I would like to, see which game reaches this sort of limit cycle, I'm not sure I could answer that. Is that the question that you're asking, though?
Yeah, I'm not going too deep here. I'm just trying to go from that previous picture to this one, because this one is kind of striking. The guy didn't get Nobel Prize for nothing, right? There is a big jump here intellectually.
I mean, I'm not sure he got the Nobel Prize for this, but yes, you're right. That
this is not trivial matter here.
Yeah, exactly. To be honest, I'm not sure how he came to this result. Perhaps Sebastian has a better understanding of that. But unfortunately, I wouldn't be able to answer that for you.
Can I maybe jump in here?
Yeah.
Because the idea of rock, paper, scissors is very clearly that, there's this cyclic idea that rock beats, I forget, paper, and paper beats scissors. And then again, so it's a cyclic idea. And so this surely was the idea behind the original thing. So that so one player is trying to copy the other player's positions, but the other player is always trying to be ahead of the other player. And so this forces kind of something periodically. And of course, this is not enough to make this formally correct. But that's for sure the intuition that Shapley had.
Okay, that helps.
Okay, thank you, Sebastian. Yeah, and any other questions just off the bat? Okay. So we looked at fictitious play just for these two player games. What I want to do is pander to the people a little bit and move towards populations, right? How do we analyze and understand fictitious play when you've got multiple agents in the environment, right? Not just two. So what I'm about to tell you is very much ongoing work, but let me dive right into it. Essentially, the way that you would look at a population, there are multiple ways. This is just the way that we looked at it, is to encode that each agent interacts with everyone else through some kind of communication network, right? So that if I'm the purple agent and I'm connected to, let's see how many, 1, 2, 3, 4, 5. Wow, I have 5 connections. Okay, that over exaggeration aside, let's say I'm connected to 5 people, right? The way that we looked at fictitious play in this particular instance is through what's called a network aggregative game. Some of you who looked at control theory literature will be familiar with the network aggregative game. It was proposed in, I think, 2015, and appears a lot in distributed control. But what we wanted to do is understand the behavior of learning on this particular model, right? Now, in the network aggregative game, what I'm going to do as the purple player is I'm going to look at the strategies, let's say P1, P2, P3, P4, and P5 of all of my neighbors, right? And I'm just going to take an average of that strategy. Okay. And now this average, what should we call it? Let's call it P tilde or something like that, right? Now this average of all of the strategies of my neighbors is the only thing that I'm interested in looking at. As for all intents and purposes, this average is my opponent, okay? And each of these 5 agents would, of course, do that with each of their own neighbors, myself included, right? But for each agent, all they view is the aggregate of their neighbors. And what that means is you can take this entire population game and just decompose it into a series of 2-player games, right? So that you can use, or at least hopefully use, the results from 2-player fictitious play and extend it towards a population, okay? So our first question is, okay, well, if we make the same zero-sum assumption that we did with fictitious play in 2-player games, we knew that it converged then, does it still converge under this new model? And fortunately, we were able to show that it does. And so what you can see in these graphs, so because we're looking at multiple agents, on the left, we're looking at 10 agents and 20 agents on the right. I've modified the representation slightly. What you're seeing is essentially the normed distance for any given agent. So each line depicts an agent. You're looking at the normed distance from its current strategy to the Nash equilibrium, right? And you can see that for 10 agents, 20, and hopefully as well, going beyond that. In fact, analytically, we know that going beyond that, you'll still converge regardless of how many agents you get. It's just that once you get past 20 agents, my laptop doesn't really like me anymore. So in these particular examples, as long as you make this zero-sum assumption, we know that the network aggregative format with fictitious play is still going to converge to a Nash equilibrium, which is a good start, right? And in fact, the proof structure for solving this problem is exactly the same as you would, or it's at least a natural extension of the way that you would do it for a 2-player game, right? So you had a Lyapunov function in the 2-player case, which was essentially the sum of the maximum payoffs that each agent could get, right? Essentially a similar Lyapunov function, except, well, I suppose I should do it as P, maybe as a tuple 1 to n. Essentially, all you're doing is working out the max payoff that each agent could get, except you're doing it for every single agent in the environment. Let's say every agent knew, right? And you take the same Lyapunov function, you can also work out that this goes down to, I should say dl dt goes down to 0, L goes down to 0, which implies that fictitious play reaches a fixed point, and of course, that means that it reaches a Nash equilibrium, right? So this still holds in the exact analogous way, even if you throw in a population, right? And so our next question was, well, if that's the case, when you have this zero-sum assumption, what about the Shapley game that we looked at earlier? Does that behave in the exact same manner? Lo and behold, the answer is yes, right? I'm sure nobody was surprised to hear that. But essentially, we looked at a 3-player example and worked on a slight variant of the Shapley game extended towards 3 players. And we found that they reach, the agents reach the exact same limit cycles that you would expect, right? Let's just focus on the left-hand graph where you can see the limit cycles directly. Now, the thing is, when you're dealing with not only social situations, but also computational design, we can't always make this assumption that everyone's going to know everyone else's strategy perfectly, right? I'm not going to know the strategies of all 5 of my friends, if I had 5 friends, all 5 of those friends with perfect accuracy. There's going to be some noise, there's going to be some uncertainty there, right? Similarly, when you're designing computational agents, you have to take into account sensor and communication noise, right? So our question was, okay, what if the average that we get here was perturbed slightly, right? This aggregate strategy of all my neighbors, what if I perturb it slightly by some noise, right? So we throw in some Gaussian noise just to look at what happens. And we found something pretty interesting, which was that when there's no noise, as you'd expect, exact same situation as we had before, fictitious play ends up converging to a Nash equilibrium, right? Again, under the zero-sum assumption. But what was interesting is when we throw in just a small amount of noise and even increase it slightly, you can see that whilst they're not converging down to the Nash equilibrium, they are settling down over time, right? So they're reaching a fixed point, but just not the Nash equilibrium of the game. And we were quite surprised to see that the dynamics settled down at all, even when you threw in a little bit more noise. But that ended up happening in every single zero-sum game that we looked at. And so what we wanted to understand is if we take the Shapley game again and throw in a little bit of noise on there, again, this is all just additive Gaussian noise. What happens under those assumptions, right? And in this case, what I want you to look at is this right-hand graph where the limit cycles correspond to these oscillations towards and away from the Nash equilibrium, right? If we look at the exact same scenario when we throw in a little bit of noise, you start off just by making the oscillations a little bit smaller, right? So that the limit cycle itself just gets a little bit tighter, right? But then as you increase the amount of noise that you put in, the whole system ends up converging, and specifically converging to the Nash equilibrium, which we found quite bizarre because what it essentially suggests is that as you add in some stochasticity, some uncertainty, the cyclic behavior breaks past a certain point and you result in convergent behavior, which anyway, we found that quite strange, and it's currently an area of ongoing work to figure out why exactly this is happening. So if anyone has any ideas as to why that might be happening, I would very much appreciate them. But that is essentially how you might be able to extend fictitious play from a 2-player situation to a population. Any questions based off that?
Maybe it's time to understand the noise better.
Sorry?
Maybe it's time, because of the puzzle you pose here, time to understand the noise better, experiment with different noise formulations.
That's actually good.
And compare the results
Yeah.
and see what is doing what. Because
so you mean like,
yeah, sorry.
so you
Go
mean
ahead,
like look with different types of maybe like multiplicative noise instead of just additive, that kind of thing, and then try and compare the different behaviors that show up.
Right, and sub-additive noise and different colors noise, because there is not only the simple Gaussian noise. And there is a notion that comes to mind here about noise that sometimes, and it's consistent with the puzzle that you show, and this is that noise can actually help you to find the signal. and you found some kind of stabilization or saturation, okay, once you introduced the noise. So there is some magic or mystery in this noise, okay? Once you put noise or uncertainty, or so the adjustment of the system to the uncertainty is helping in a way, as the result is showing.
Yeah, I think I like your point about looking at various types, especially like various colors of noise, because you're right, there is almost something strange that's going on within adding in some uncertainty. What we'd really like to do is understand why that's happening. And your point about essentially noise helping you find the signal, which I think you're framing like an information theoretic sense. I think that makes a lot of sense. It's almost like, I guess, moving away from local minima in like an annealing sense and finding some kind of global optimum.
Yeah, as an entertaining note here, if the fridge is not working well, sometimes instead of calling the expert, you just kick it and it comes back. So, all right.
Okay, that makes sense. Anyway, are there any other questions just off the population stuff? By the way, I can't read the chat from at the end, so if there are any in there, please do let me know.
Yeah, no, there are no questions. No.
Okay, so then in that case, what I'm going to do is move on to reinforcement learning. And I realized that I've gone for quite a while on fictitious play. So since I'm aware that many of you are working in machine learning itself, so I imagine you're all really familiar with reinforcement learning. So I'm going to zoom through the motivation behind it and get on straight into the meat of the results themselves. Okay, so reinforcement learning, in particular, the model that we're going to be looking at it, Q-learning, revolves around this idea that agents have a certain belief of what actions will do well and what actions won't. And then they update those beliefs as they receive rewards or they essentially gain experience, right? This is probably a diagram that you guys have seen multiple times in every machine learning lecture or reinforcement learning lecture that you've attended. But specifically what works with when you're dealing with multiple agents is not only does an agent have to react to the environment as an external body, just the environment itself, but also the other agent is part of any given agent's environment, so to speak, right? So it's a non-stationary problem in the sense of you're not only reacting to a stationary world, let's use the word world instead of environment, but also reacting to a non-stationary opponent who is going to adapt alongside you, right? Now, the way that reinforcement learning or Q learning does this is that each agent is going to assign a Q value, right? A Q value essentially being a measure of the quality or the perceived quality of an action. This is how good I think this action is going to perform, right? And now, at each time step, the agents are going to follow the following steps. They're first going to choose an action, right? So let's say they both choose to confess. This is the prisoner's dilemma game, by the way. Let's say they both choose to confess and they receive some kind of reward, right? The reward given by the payoff matrix. What they're going to do then is they're going to update their Q value, the perceived quality of an action. And then they're going to keep repeating this process. So they update their Q values as they go along, and eventually they reach some kind of, hopefully, they reach some kind of steady state in which they say, okay, these are my perceived qualities of the action, and that's how I'm going to choose my actions from here on out. Okay. Now, again, we have to take all of this and make it a little bit more rigorous. So the two steps that an agent is in control of is choosing the action and updating the perceived value of an action, right? The reward itself comes from the environment, so the agent doesn't have much control over that. Okay, so let's have a look at each of these two steps. The first step being choosing, why did I write 10? The first step being choosing an action, and the second step being updating the Q value or your perceived quality of an action, right? Now, the particular model that we're going to be looking at is Q learning using a Boltzmann distribution. Those of you who've studied reinforcement learning will have come across this. But essentially, it works as follows. The probability by which each agent, whether it's agent 1 or agent 2 on the right, picks some action I, is going to be some function of their perceived quality of the action, which is given by the Q value, right? And this beta parameter, right? And we'll explain what the beta parameter means in a second. And then finally, you divide it through by this partition function Z, which just means that everything normalizes to 0. This is also a softmax function for those of you who look at it in that sense. Now, the second question that we have to ask ourselves is, okay, where does this Q value come from, right? We also need to look at beta, but let's look at Q first. The Q value, as I said, is initialized, and then as an agent's initial belief of how well actions are going to perform. And then as the agents receive their reward, which is given by the payoff matrix, the agents are going to update their actions, their perceived quality of the action. Okay. Now there are two parameters that we need to take into account here. The first is alpha that appears here, and the second is beta, which we'll explain in a second. But alpha is essentially a step length, right? So that if alpha is really low, an agent almost prefers their previous knowledge, or the agent is almost a little bit more stubborn, a little bit more unwilling to respond to new information. Whereas if alpha is quite high, then new information is preferred over my previous beliefs. And therefore, I'm going to respond a little bit more reactively to the reward that I get at every single time step. Okay. So the step length basically just gives you a way to moderate between those two extremes. Similarly, beta corresponds to the standard exploration-exploitation parameter in reinforcement learning, which essentially says that I can either exploit actions that do well, that I currently think do well, or I can explore and hopefully find actions that perform better over time, right? And this beta parameter essentially allows you to shift between those two extremes. Okay, so those are two parameters that we have in this, but everything else revolves around this discrete time algorithm that we've been looking at. Now, again, in the exact same way as we did with fictitious play, I'd like to move from discrete time to continuous so that we actually have a dynamic that we can understand, right? And this was work that was done I think, independently by two authors. The one that I'm showing here is by Carl Toyles. There was another one in 2005, I think, or maybe 2006, which derived pretty much exactly the same model by James Crutchfield. But anyway, let's focus on the dynamic itself because it's the same for both authors. There's a whole derivation that goes into moving from the discrete time algorithm to the continuous time. It's not as easy as it was with fictitious play, so I'm going to skip over that here. And because I've skipped over it, what I'd like to do is just convince you experimentally that this works, right? So what I've got on the right-hand side, on the top, I'm plotting or at least the authors, this is taken from their original paper. What the authors did is plot the trajectories that are predicted by the Q learning dynamics that they were able to derive. And on the bottom, they actually applied the Q learning algorithm. And you can see that this is for the prisoner's dilemma game, by the way, that the agents end up converging exactly to the equilibrium that's predicted by the dynamical system, or the ODE, right? So that's my quick empirical, hopefully convincing you of the fact that this dynamic works. Of course, if you want to know how it's derived, those are in the set of notes that accompany these talks. But another thing that I want to point out about this particular differential equation is that there's two components to it, right? If we kind of ignore the alpha and tau for a second, right? There's two terms. One is this left-hand term, which some of you will recognize as the replicator, like it's essentially the replicator dynamic. If we just ignored this term for a second, what we're left with is replicator itself, right? And that kind of encodes the rational part of the agent who likes to maximize their payoff, right? So the exploitative part of the agent. And that's balanced by the second term, which some of you may recognize as an entropic term, right? Which essentially encodes the explorative part of the agent, right? The agent that doesn't necessarily always make the rational decision, but likes to randomize as well, okay? So Q-learning essentially gives you a balance between these two extremes. And these are all dependent on these parameters, alpha and tau. By the way, Toyles used tau in their paper. I used beta. It's just a matter of preference. Both are completely equivalent. But these two parameters allow you to move between the exploitation part and the exploration part, right? So since there's such a similarity to replicator, let's have a look at the behavior of Q-learning on something that we already know from the replicator dynamic, right? We're looking at the matching pennies game again, which was a zero-sum game, right? But in particular, it's a two-player, two-action game, right? And we saw beforehand that replicator reached these periodic orbits, right? And in fact, we went even further in the previous talk to say that replicator was a conservative system, i.e. it conserves energy along its trajectory, right? And because of that, because of the fact that it conserves the abstraction of energy along its trajectories, we know that the agents will follow this periodic behavior, right? In exactly the same way, Q-learning is a dissipative system. So it dissipates energy or the abstraction of energy along its trajectories, right? And you can use the exact same energy functional that you use for replicator and apply it to Q-learning, and you can see that it's dissipated along trajectories of Q-learning. And what that tells us for two-player, two-action games is that we will always reach an equilibrium. Whether it's zero-sum or not, we know that two-player, two-action Q-learning will always reach an equilibrium, okay? Now, the difficulty with that is most games that we actually care about aren't going to be two-player, two actions, right? So the question of does reinforcement learning or Q-learning maintain this behavior as you move from, you know, the simple example to much more complicated example, that is very much an area of ongoing work. It's not been established yet whether this is always going to be the case, but let me give a little bit of a taster on what has been established so far, right? This is a work that was done in 2018, in which the authors were looking at a slight variant of reinforcement learning called experience-weighted attraction. Now, don't focus on the different name. Essentially, it's just a question of which community you come from. Experience-weighted attraction is a pretty common algorithm to be analyzed in economic literature, whereas Q-learning is applied a lot in computational literature, like machine learning literature, right? They're effectively the same algorithm, so let's ignore the differences between the two. But what the authors were looking at is how often do we get convergent behavior versus complex or even chaotic behavior when we apply this reinforcement learning scheme, okay? And so on the left-hand chart here, I don't want you to focus too much on the axes themselves, but what I do want you to focus on is this hot region, right? This hot region essentially denotes the cases in parameter space for which reinforcement learning gives you chaotic or complex behavior. And this darker region is where the behavior was convergent, okay? Right, so you can see that, when you have just two players, there's quite a lot of convergent behavior that's happening, right? But what's interesting is as you move from two players to a higher number, they haven't even gone that far, they've only gone up to 5 players, but you can see that this complex region or this chaotic region is really starting to take over phase space, right, or parameter space, which means that the likelihood, or what they call the prevalence, of chaotic dynamics increases as you increase the number of players in the game. And you can see this even more directly on this second chart, where essentially they view only the influence of the number of players in the game, and they look at what the area of this unstable, this chaotic region is as you increase the number of players. And you can see that it's like almost a logarithmic increase. It's definitely a monotone increase in function, to say that as you increase the number of players, you're really going to be getting much more chaotic behavior. And this is obviously really interesting, but from a design or a computational perspective, it's kind of annoying, right? Or even an economic perspective, it's kind of annoying, because what we'd like to do is either predict what the outcome of a particular game is going to be, or we'd like to design a game to have the outcomes that we would like it to have, right? If we designed a multi-agent system and we didn't know what it was going to do, well, that's not a very safe situation to be in, right? Stuart Russell would not be very happy with that. So we'd like to know what the outcome is going to be. And what this is telling us is, once you move to a higher number of agents, which is where the interesting stuff happens anyway, you're losing your ability to predict or to design systems in a sense that you would like them, design systems whose outcome you would like to know a priori. This was, I can't remember who it was who mentioned this, but this is called the Tragedy of the Masses, which is just a title that I absolutely love in the previous talk. And it's a very real problem when you're trying to design population-based systems, which is why things like understanding behavior on networks is much more, is quite useful, because it allows you to constrain down the problem a little bit. It's also why looking at what are called mean field populations, where essentially you take the number of agents straight to infinity and analyze it there instead, is much more useful, because at least there's some tractability in that problem. And that's the sort of thing that we're going to be looking at in the next talk. So I hope you enjoyed this one, and I hope to see you for the next one. Are there any questions based on what we've said so far?
Yeah, if you have time.
Mm-hmm.
There was one picture before in the last zero sum. Yeah, this one. Mm-hmm. Now the spirals not here is now going out. It's not going in. It's like no expression of the non-convergence.
No, sorry. These spirals are going in. The initial conditions are out here, and then they all spiral in towards. I should have made that clear. Sorry.
Okay, my mistake. The other question is, can I use what I heard from you to understand better bargaining theory or bargaining situations or conflict resolution when you have one agent very stubborn and so on?
Well, what do you mean by understanding this sort of situation?
Well, I like to apply this, okay? So the results that you show are very clear-cut results. Now, there are real-world situations where things are very far from clear-cut.
Yeah.
Okay, like even in family, they start with super love, and then they, in some situations, come into a bit, in quotes, conflict.
Yeah.
So can I translate these real-world situations via game theory perspective to design a better solution.
So the theoretical part of me wants to say yes. You can, model this. Let's use your family example into, a series of payoff matrices where everyone is interacting with everyone, and what their incentives are, etc. Right? And then apply the results of these dynamics and say, okay, I think you're going to adapt according to some version of reinforcement learning. So let me see what the outcome of that is going to be, and how I might, change your incentives. This is a big part of game theory, which is how can I change the incentives to give me the outcomes that I want, right? It's called game design or mechanism design, right? So theoretically, that's possible, right? And there have been works that look at that particular issue of, if we assume a particular learning dynamic, how can we design the game in order to, or change the incentives in order to give the outcome that we want. However, what this last result that I have here on the prevalence of chaotic dynamics, this result from 2018, is saying is that as you increase the number of agents that you're dealing with, it's becoming increasingly more difficult for you to be able to design a game that is that gives you the outcome that you want, right? Because the whole notion of chaos is that if you take two, or at least a heuristic definition of chaos is if you take two initial conditions close to one another, they can become arbitrarily far apart as you iterate, right? So that means that you can design your game, but if your initial conditions are slightly off, if you have, what is this, a 5-player game, that's about the size of a normal family, right? 4 or 5 people. Even that, if you just start your initial conditions just slightly off, or you get them slightly wrong, the whole outcome is going to change, right? Which makes the mechanism design problem really, really difficult, especially when maybe you add in the extended family. Now things are becoming even more complicated. And so the practical part of me is saying, I don't think it's always going to be the case, or necessarily ever going to be possible that we can exactly design a game that gives us the outcome that we want.
Yeah.
Unfortunately.
Yes.
But actually, now that's aside, I should mention that this particular result that you're looking at here, this thing about prevalence of chaotic dynamics, this was assuming that all agents are interacting with one another, right? So I'm playing a game against absolutely everyone in the population. Now, the issue with that is that that's not always going to be the case in reality. Most of the time, we interact, like we had before, through some kind of a social network. And the reason why I didn't put this in, but this is very much ongoing work where we're looking at what the same situation, the same model of chaotic dynamics when agents are constrained to interact on a network. And what we're finding is that now you're dealing with much more convergent behavior, much simpler behavior in a sense, where even if you throw in 20 actions, even if you throw in 10 agents or whatever, you're still getting some kind of convergence, whether that's to a limit cycle or to a fixed point. You're not getting these chaotic dynamics as often. So if that result holds generally, and hopefully it does, then there might still be some hope for designing population systems that give us the outcome that we want.
Okay,
I hope that answers your question.
Yeah, absolutely. Very nice.
Are there any in the chat, Timothy?
No, there's no other questions.
Okay.
All right.
Hello.
Then, so I think there are. Oh no, there is a
Yes,
question. Someone is talking.
Yes, I have a naive question.
Mhm.
How can you apply game theory to the building of a vaccine for COVID-19? it's a kind of game that you play with this virus, right?
Okay, so that's actually a really interesting question, because there's a number of different ways that you could go with this, right? Are you asking about like how you might design a game treating the virus itself as an agent, or how might you design a game so that, you know, treating individuals as the agent but acting in the environment of COVID? Does that make sense?
Yes.
So
Yeah.
is your question about treating the virus as an agent, or treating everyone just acting in the environment of COVID?
The first type.
Oh, that's a really interesting one. Actually, that one I haven't thought about. I know there's been some works that look at this particular problem. I haven't looked at it myself, but oh, that is actually really interesting, because what you might consider is modeling the virus as an agent as, you know, the only incentive is to transmit, right?
Mm-hmm.
And then, yeah, actually, so if the virus is an agent that you would only consider interested in transmitting, but then you also have other agents in the population, right, who can interact with one another. The question then is, how do you set up the incentives of all of the individuals so that the virus isn't able to transmit, if that makes sense?
Yes.
I feel like that could be modeled in a very game theoretic sense, where you treat the virus as almost like a leader in the system, and the other agents, i.e. the people, as followers. So they have to react to the behavior of the virus. And so now you get a leader-follower game, all mapped out with their own incentives, and then work out various, you know, adaptation protocols for that. That's just off the top of my head. I haven't looked at this rigorously at all. But yeah, that's just a naive answer to your question.
Okay, thank you.
Actually, another interesting point about that is looking at how you might model agents acting in the environment of COVID. So for example, let's say you want to incentivize people who they all want to go out to a particular venue, right? Let's say everyone wants to go out to the pub once things have lifted, which they have now, of course. But you would like to incentivize it so that people don't want to go to a particular venue if there are already a lot of people in there, right? Does that make sense? So the idea is that if there's already a high density of people in a particular venue, a person would want to go to another venue, right? This is what's called a minority game, so that each agent wants to be in the minority of the population. And that actually has quite a lot of literature behind it from the statistical physics community, looking at what the outcome of the game would be. So that might be, that might give a good answer to your question.
Right. Okay. Thank you.
Felix, did you want to say something, or? Yeah, okay, yeah, so Felix wrote a comment on the chat, but
oh, okay, sorry.
it just like wrote, I mean, it was related to the discussion. The virus wants to destroy your gene.
Right.
Yeah, anyway, I mean, if you want to say something else, or yeah, okay.
Honestly, I've actually been, that's really piqued my interest. The question of modeling.
Nice idea, actually. Yeah.
Yeah.
I wonder if maybe decision makers are already thinking about, I mean, along these terms. That is, yeah.
Yeah, because especially this notion that we have to react, like the virus itself is almost an independent agent that makes a quote unquote decision to mutate, and we just have to react to that behavior. So modeling it in a reactive sense could be quite interesting.
Yeah.
Anyway, are there any other questions just on the chat or in general?
No, I think just Sebastian posted the notes, so I just like posted the notes also on the YouTube channel. Yeah, thank you, Sebastian.
Perfect. Thank you.
Yeah. Yeah, all right, okay. Yeah, thank you very much. I think we'll probably next session in about 2 weeks or something. Yeah, something like that.
Okay, thank you.
Okay, thanks a lot. Thank you. Take care, everyone. Thanks, Aamal again. Thank you.
Bye.
Bye.